There's something almost poetic about watching raw steel transform into precision machinery. Today we're inside Cymex Engineering, where they're forging the heart of their CBE crusher bucket, a massive shaft that'll spend its life doing the tough work most of us never see. Now, if you've ever worked a construction site, you know crusher buckets are game changers. They attach right to an excavator and pulverize concrete and rock on the spot. No hauling debris across town. But here's the thing. That shaft spinning inside takes a beating like you wouldn't believe. That's why Cymex starts with forging. They heat the steel white hot and hammer it into shape, aligning those metal grains for maximum strength. It's old-school metallurgy meeting modern needs. After forging, the shaft moves to CNC machines for cold machining, computer-controlled precision that shaves it down to exact tolerances, sometimes within thousandths of an inch. This two-step dance, forging for toughness, then CNC for accuracy, creates a shaft that laughs at torsional stress and shear forces while grinding through rubble day after day. Let me tell you about a small piece of brass that's been at the center of American music for generations. The Bach trumpet mouthpiece. If you played in your high school band or listened to jazz on a summer evening, you've heard its voice. The mouthpiece is where magic begins. Your lips buzz against it, and somehow music happens. But not just any mouthpiece will do. Bach has been the gold standard since the 1920s, and there's a reason why. Each one starts as a solid chunk of brass. Modern CNC lathes spin and carve with incredible precision. We're talking microns here, shaping that critical cup where your embouchure meets metal. The geometry matters enormously. Too shallow and you lose warmth. Too deep and you sacrifice clarity. After machining, skilled craftsmen hand polish each piece until it gleams, then apply silver or gold plating. Now here's a tool that's probably saved more knuckles than we can count. The Beta Model 42 combination wrench. Open end on one side, box end on the other. Simple, right? Well, not quite. If you grew up turning wrenches in your dad's garage or spent decades in machine shops, you know the difference between a hardware store wrench and a real tool. Beta's been making these in Italy since 1923, and the Model 42 is their best seller for good reason. What makes these special is something you can't see. It's in the steel itself. Beta starts with chrome vanadium alloy, carefully selected for its ability to flex just enough, without bending permanently. See, when you're torquing down a stubborn bolt, you need a wrench that won't twist out of shape, or, worse, snap and send you into whatever you're working on. The manufacturing process is where science meets craftsmanship. First, they forge the basic shape, heating that steel and pressing it under tremendous force. This isn't just about shaping. Forging actually aligns the molecular structure, making the metal tougher than if you just cut it from sheet stock. But here's where it gets interesting, the heat treating. They heat these wrenches to precise temperatures. We're talking about 500 degrees Fahrenheit or more, then quench them in controlled conditions. Too fast, and the steel becomes brittle like glass. Too slow, and it stays soft. Beta's metallurgists have this down to a science, creating what they call the sweet spot. Hard enough to resist wearing down, but tough enough to handle shock loads. After heat treating comes the tempering, which is really the secret sauce. They reheat the hardened wrenches to a lower temperature, which relieves internal stresses and adds ductility. It's this balance that lets a Model 42 handle high torque without snapping. Then there's the finish machining. Each wrench gets precision ground to ensure the box end fits perfectly. No slop, no rounding off bolt heads. The open end is milled to exact angles. They even control the thickness. Beta's famous for making their wrenches slimmer than most competitors, so you can get into tight spaces, but they never sacrifice strength. Quality control is relentless. Every batch gets tested. They'll actually torque test samples to destruction to verify they meet standards. We're talking about applying forces that would twist lesser wrenches into pretzels. You hold a Model 42, and you're holding a century of tool-making knowledge. It's the kind of tool you buy once, use for 30 years, and pass down to your kids. In a world of disposable everything, there's something reassuring about that kind of quality. Let's talk about building big things. Specifically, the tanks and pressure vessels that hold everything from water to industrial chemicals. Well, that's where machines like the BMB25 dishing press come in. Picture this. You start with a flat, round piece of steel plate, maybe 8 feet across, maybe 12. Your job is to turn that pancake into a smooth, curved dome. Sounds simple until you consider that steel doesn't exactly want to bend uniformly, especially when it's 3/4 of an inch thick. The dishing press is an impressive beast. At its heart is a massive hydraulic system that can exert hundreds of tons of force. The process is almost mesmerizing to watch. They position that flat steel disc on the lower die. Then the upper die, shaped like a huge dome, descends slowly but with incredible force. Here's what's fascinating. It's not a sudden smash. The press applies gradual, controlled pressure, literally flowing that steel into shape. You can almost see the metal reluctantly giving up its flatness, forming around the die like it's being taught a new shape. Modern presses like the BMB25 have computerized controls that monitor the pressure constantly, ensuring even forming without cracks or weak spots. But the dishing press doesn't work alone. After the dome is formed, it moves to the flanging machine. Think of it as the press's partner. The dome at this point has smoothly curved walls, but no straight edge to weld to the tank's cylindrical body. That's the flanging machine's job. The flanging operation is where precision really matters. The machine grips the dome's edge and rolls it, creating a perfectly flat rim all the way around. This rim needs to be dead-on perpendicular to the dome's axis, or you'll never get a good weld. We're talking about tolerances measured in fractions of a degree, over a diameter of several feet. It's this partnership between dishing and flanging that's been building America's industrial infrastructure for generations. Every water tower in your town, every propane tank behind a restaurant, every pressure vessel in a refinery, they all started with this process. Springs are everywhere, aren't they? From the pen in your pocket to the suspension on your truck, they're quietly doing work we rarely think about. But making a spring, a really good spring, takes more precision than you might imagine. Modern CNC spring coiling machines are fascinating pieces of equipment. If you've ever tried to wind wire by hand, you know how tricky it is to keep consistent coils. Now imagine doing it with wire that might be thick as a pencil, winding it into springs that need to compress exactly the same way, thousands of times. These machines start with wire fed from large spools. The wire runs through precision guides and rollers that straighten out any kinks, because even the slightest bend affects the final spring's performance. Then comes the magic. Computer-controlled fingers and pins literally sculpt the wire in real time. For compression springs, the kind you'd find in valve assemblies or mechanical keyboards, the machine winds the wire around a mandrel while controlling pitch with incredible accuracy. The computer adjusts tension and positioning dozens of times per second. Tension springs need hooks or loops at the ends, and watching the machine form these is like seeing a metal artist at work. It bends, twists, and cuts, with motions faster than you can follow. Torsion springs, which provide rotational force like in clothespins or clipboards, require the machine to wind the coils tight together, then form legs at precise angles. What used to take a skilled craftsman hours now takes minutes, with repeatability that human hands simply can't match. It's automation done right, not replacing craftsmanship, but extending it. Solingen, Germany. For centuries, this city's been synonymous with one thing: blades. And if you've ever held a real chef's knife, chances are you've heard of Wusthof. It starts with forging. Unlike cheaper knives stamped from sheet metal, Wusthof heats their steel to glowing orange and hammers it into shape. This isn't just tradition. Forging actually compresses and aligns the steel's grain structure, making it denser and more durable. Next comes heat treating, the critical step. They heat the blades to over 900 degrees Fahrenheit, then cool them in a precisely controlled process. This hardens the steel, but here's the trick. They temper it afterward, reducing brittleness while maintaining that razor edge potential. Then the grinding begins. Skilled workers shape each blade's profile and taper. The edge isn't just sharp, it's geometrically precise, ground to specific angles that balance cutting ability with edge retention. Laser etching comes next, burning the Wusthof Trident logo into the blade. It's permanent, precise, and adds that mark of authenticity. Finally, the sharpening. Expert craftsmen hone each edge to hair-splitting sharpness on specialized wheels.